For as long as we've gazed at the night sky, we've wondered, are we alone? Every star is a potential sun, each with its own family of worlds, some perhaps like our own. The search for exoplanets, planets orbiting other stars, has become one of science's greatest adventures. Just decades ago, finding even one was science fiction. Now we've confirmed thousands. Each new discovery helps us understand how planets form, evolve, and what makes a world habitable. Are the conditions for life common or rare? To answer, we look outward, gathering clues from distant worlds. We build ever more powerful telescopes to peer deeper and analyze the faint light from these alien planets. We're no longer just asking if other planets exist, we're asking what they're like. What's in their atmospheres? Do they have the building blocks of life? These questions drive our endless quest among the stars. To answer these questions, humanity needed a new kind of eye, one capable of peering deeper into the universe than ever before. Enter the James Webb Space Telescope, or JWST, a marvel of modern science and engineering. Webb orbits 1 million miles from Earth, far beyond the reach of our planet's shadow. Its enormous golden mirror, made of 18 hexagonal segments, is designed to gather the faintest whispers of cosmic light, capturing details invisible to any previous telescope. In many ways, Webb is a time machine. It allows us to look back billions of years, seeing galaxies as they formed just after the Big Bang, offering glimpses into the universe's earliest moments. But Webb's true genius lies in its ability to see in infrared, light that's invisible to our eyes, but absolutely crucial for unlocking the universe's deepest secrets. This lets us peer through cosmic dust that would otherwise obscure our view. Infrared vision allows Webb to pierce dense dust clouds, revealing stellar nurseries where new stars are born. It also lets us study the atmospheres of distant exoplanets, searching for signs of habitability. When a planet passes in front of its star, Webb analyzes the starlight that filters through the planet's atmosphere. This technique reveals the planet's chemical makeup, including the presence of key molecules. Webb can detect water vapor, methane, and carbon dioxide, gases essential for life as we know it. These discoveries help us understand which worlds might be capable of supporting life. Before Webb, exoplanets were little more than faint points of light. Now, for the first time, we can study their features, chemistry, and even their climates, transforming them from distant mysteries into real, dynamic worlds. Webb is our Galileo's telescope for exoplanets, giving us our first detailed views of these distant worlds and opening a new era of discovery. It's a revolutionary leap for astronomy, already rewriting what we know about planets, their atmospheres, and the possibilities for life beyond Earth. For years, we sorted planets into neat categories: rocky worlds, gas giants, ice giants, and new types like hot Jupiters and super-Earths. But the universe is more imaginative than our labels. In 2025, Webb's data hinted at a new class of planet, worlds that don't fit any known category. These aren't just oddballs, they're fundamentally different, with properties once thought impossible. Imagine a planet with the mass of a gas giant, but an atmosphere unlike anything we've seen, or chemistry that defies our models. The clues are tantalizing, suggesting gaps in our understanding. Finding something that doesn't fit is often more exciting than finding what does. It means our theories are incomplete. These mysterious worlds challenge the foundations of planetary science, forcing us to rethink how planets form and evolve. They're not just new dots on a map, they're new puzzles that could transform our understanding of the galaxy. One of Webb's most spectacular achievements is the detailed study of WSP-18b, an ultra-hot Jupiter that's not only 10 times more massive than Jupiter, but also orbits incredibly close to its parent star. This makes it a fascinating and extreme example among the thousands of exoplanets discovered so far. WSP-18b completes a full orbit around its star in just 23 hours, less than a single Earth day. Its proximity means it's blasted by intense stellar radiation, making its environment unlike anything in our solar system. The planet is tidally locked, so one hemisphere is always facing the star, bathed in perpetual daylight, while the other side remains in endless freezing night. This creates a dramatic contrast between the two sides, with extreme temperature differences. For the first time ever, astronomers used Webb's powerful instruments to create a full 3D map of this distant planet's atmosphere, revealing its structure in unprecedented detail. The technique, called eclipse mapping, works by isolating the planet's light as it passes behind its star. This allows scientists to measure subtle changes in brightness and tease out information about the planet's temperature and atmospheric chemistry. By repeating this process over multiple orbits, scientists were able to build a global weather map for a world located 400 light-years away, tracking how heat and clouds move across its surface. Webb didn't just map temperature, it also mapped the distribution of molecules like water vapor and carbon monoxide across the planet, providing a chemical fingerprint of its atmosphere. The result is a stunning portrait of an alien world, with dayside temperatures soaring to nearly 2,700 degrees, hot enough to vaporize metals, and a night side that's much cooler, shrouded in darkness. This ability to probe exoplanet atmospheres in 3 dimensions is a true game-changer for planetary science, opening up new ways to understand how these distant worlds work. We can now study atmospheric dynamics, wind patterns, and chemistry in ways never before possible, unlocking secrets about weather, climate, and even the potential for habitability on other worlds. WSP-18b is just the beginning. This revolutionary technique will open new doors across the galaxy, helping us map and understand countless other exoplanets in the years to come. Webb's 3D map of WSP-18b revealed surprises that challenge our models. The dayside showed an intense hotspot, more concentrated than expected, suggesting something is slowing the winds that should spread the heat. Surrounding the hotspot was a cooler ring, creating a dramatic temperature gradient unlike anything in our solar system. The cause may be powerful magnetic fields interacting with the atmosphere, something our models don't fully explain. But the biggest surprise was chemical. The hottest part of the planet had far less water vapor than the cooler areas. At extreme temperatures, water molecules are torn apart, a process called thermal dissociation. On WSP-18b, we're seeing this happen for the first time, confirming a key theoretical prediction. This defines a new subclass, ultra-hot Jupiters, where chemistry is fundamentally altered by heat. The water isn't just boiling, it's being ripped apart, creating a truly alien atmosphere. While Webb mapped distant giants in the far reaches of the galaxy, its gaze also turned closer to home, searching for new worlds in our cosmic neighborhood. It focused on our nearest stellar neighbors, the Alpha Centauri system, a fascinating trio of stars just over 4 light-years away, making it the closest star system to our own sun. In August 2024, astronomers detected a faint, elusive heat signature, a possible planet, dubbed S1, circling Alpha Centauri A, using Webb's powerful mid-infrared instrument to peer through the glare. Detecting this signal was like spotting a firefly next to a searchlight, requiring advanced techniques and a coronagraph to block out the overwhelming starlight and reveal the hidden world. However, when astronomers returned for follow-up observations in 2025, the planet was nowhere to be seen, leaving the scientific community puzzled and intrigued. This disappearance might simply mean S1 was hidden in the star's intense glare, possibly due to an elliptical orbit that took it too close to Alpha Centauri A for Webb to spot. The evidence, while not yet conclusive, is tantalizing. S1 could be a Saturn-mass planet, orbiting its star every 1.5 to 2.5 years, making it a unique find so close to home. The next crucial observation window is set for August 2026, when S1 should emerge from the glare and, if real, become visible once again to Webb's instruments. The astronomical community is waiting with bated breath, eager for the chance to confirm or refute this extraordinary candidate. Confirming a planet in Alpha Centauri would be a landmark moment, one that blurs the line between science fiction and reality and inspires new dreams of interstellar exploration. It would be the closest exoplanet ever discovered, a world orbiting the star system next door to our own. Such a discovery would make Alpha Centauri a prime target for future exploration, and perhaps, one day, the first destination for humanity's journey beyond the solar system. What makes S1 so fascinating isn't just its proximity, but its location in the habitable Goldilocks zone of Alpha Centauri A. This is the region where temperatures are just right for liquid water, a key ingredient for life. S1 itself is a gas giant, likely lifeless, but gas giants often have moons. In our solar system, moons like Europa and Enceladus may harbor subsurface oceans. If S1 has large rocky moons, they could be prime candidates for life, receiving warmth from the star and tidal heating from the planet. This scenario, long imagined in science fiction, could be reality next door. The implications are profound. Habitable real estate might not be limited to Earth-like planets. Habitable exomoons could be common, vastly expanding our search for life. S1 forces us to broaden our perspective. Life might be found on moons, not just planets. The search for life is bigger and closer than we ever imagined. Webb's discoveries are reshaping our theories of planet formation. For decades, our models were based on our solar system, small rocky planets close in, gas giants farther out. The discovery of hot Jupiters upended this, showing giants can migrate close to their stars. Now, Webb's findings, like WSP-18b's extreme chemistry and S1's possible orbit, add new complexity. Our models struggle to explain these worlds, especially in binary star systems like Alpha Centauri. Each new discovery is a black swan event, forcing us to rethink and refine our theories. Webb isn't just taking pictures, it's stress-testing our understanding of how worlds are made. We stand at the dawn of a new age of discovery. Webb's 3D mapping of exoplanets is just the beginning. We'll soon build a library of alien atmospheres. The search at Alpha Centauri is only starting, with new telescopes like the Nancy Grace Roman Space Telescope joining the hunt. Imagine a future where we know hundreds of worlds in detail, planets with seasons, oceans, and even signs of life. These discoveries will transform distant worlds from abstract targets into real places. This knowledge will change how we see our own planet, its uniqueness, and its place in the cosmos. Ultimately, this journey is about more than science. It's about our place in the universe and our future as explorers. The knowledge that we live in a galaxy filled with worlds will inspire new generations to reach for the stars. The discoveries we make today are the first steps on a journey that will change not just what we know, but who we are.